Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi again, everyone. So let's continue the discussion on sketching the root locus. Now we're going to look at the case when the poles or zeros are complex. So this means that the poles and zeros have the imaginary part. Before we just look at the case when most of the cases that we have looked before, the poles and zeros only have the real part. So in order to do that, let's look at this slide again. I've explained this in the previous video, where if you have a point at the root locus, then if you draw a vector from zeros and poles to that particular point, then if you add all the angles made by the vector to that particular point, angle of the zeros minus the angle made by the vector of the poles, then you will see that the summation of the angle made by the zeros minus the angle made by the poles will be a multiple of 180 degrees. So in this case, what we're going to do is, if we have a point, when we have a pole that is complex, so here we have a case when we have a pole that is complex. Normally, we want to know how the locus leave this particular pole. If you recall earlier that the locus will start from the pole and end at zeros. So in this case, we are not we need to know how the locus leave this particular pole. Okay, is it like 45 degrees or is it 270 degrees? So how do we calculate this situation? Here is, we assume a point here which is assumed very close to x, and we draw the vectors from all the poles and zeros, and we use the relationship before. Okay, so for example, in this case, assuming there's a theta 1 here, theta 4 representing the angle made by the vectors from this particular pole, theta 1, this is theta 4, theta 5, and then same thing we can do for the zeros. Okay, so the zeros we use positive, theta 2, theta 3, theta 6, this is theta 2, this is theta 6, theta 3, and the angle made by the poles, theta 1, theta 4, and theta 5. So the angle made by the poles, we use the negative sign, we add them up. Okay, so that means the angle made by the vector of zeros minus the angle made by the vector of the pole should be a multiple of 180 degrees. So what we can do is we will solve. If we want to find the angle of departure, that is the definition of how the locus leave this particular pole. Okay, so we will solve for that particular angle. So in this case, we want to solve for theta 1. Okay, this is similarly, if you want to find the angle of arrival, in this case you have a complex zero. Okay, so you want to know how the locus end up in this particular zero, in what angle. So again, you use the same equation. You draw the vectors from all the poles and zeros, you label the angles, so the angle of zeros minus the angle of poles should be a multiple of 180 degrees. So what you can do is, you need to calculate all the other angles, but here you leave the angle, for example theta 2, you solve this particular angle by letting it to be unknown, theta 2, but the rest you find it and you subtract with 180 degrees. Just to summarize before we do the example, the departure angle for a complex number will be theta d is equal to 180 degrees minus the sum of theta p minus theta z. So we rearrange the equation and you can solve for the departure angle, right? So let's look at an example. Given the unity feedback system, find the angle of departure from the complex point sketch the root locus. So basically we want to sketch the root locus for this particular system. We have the open loop transfer function. Notice that now we have So what is this value? This is s squared plus 2s plus 2. Later on, you will see that this will give two complex poles. Okay, so let's try to have a look at this particular example. Okay, let's try to sketch the root locus for this particular example. So you can see here that we have the poles and zeros. Okay, how many poles we have? Okay, 3 poles. This comes from the s squared plus 2s plus 2. We have one pole at minus 3. We have 1 0 at minus 2. Okay, so let's just sketch the poles and zeros in just this axis. So 1 0 at minus 2, and then the two complex poles, minus 1 plus minus g1. Okay, so let's label the location of the locus on the real axis. Remember the rule where the locus will exist to the left of odd number of real poles or zeros and zeros. Okay, so I've marked the location where the location where the locus should exist in the real axis. So that part is easy, where the locus will start at the pole of minus 3 and at 0 of minus 2. But how does so what would happen to the case when we have a pole at plus minus 1, sorry, minus 1 plus minus g1. So we need to calculate the angle of departure. We don't have the idea yet. Okay, but for sure here, the end of the locus will be at zeros at infinity. Okay, so you have to calculate the asymptote. Okay, so let's use the asymptote formula as we have discussed before, given here. Okay, 2k plus 1 times 180 degrees times the number of poles minus the number of zeros. So we have 3 poles and 1 0, so 3 minus 1 is equals to 2. So this equation will calculate the angle of the asymptote. You just substitute k equals to 1, k equals to 1. So you will get the angle made by the asymptote to be 90 degrees and 270 degrees. So we need to also find the center of the asymptote. Okay, using the other equation, sigma E is equals to the sum of zeros and poles. Okay, this is the poles minus 3, this is the pole minus 1 plus g1. So you add all the poles minus the zeros divided by the number of poles minus the number of zero. This will give you the center of the asymptote, so at minus 1.5. So you can mark the center of the asymptote, and then you you can start sketching the asymptote, angle 90 degrees and 270 degrees. So that's basically a straight line at that particular point. Right? So now you know that these two poles will approach, as k approaches infinity, it will approach these two asymptotes. But at what angle will the locus leave the pole? So that's where we use the new rule. Okay, so we have to draw the vectors made by the other. So we want to find the angle of departure at this particular point. Oh, before that, are there any breakaway points? Okay, there's no breakaway points because there's no poles. The only locus are here. So then there are no breakaway points. If there there are two poles at the real axis, then we have the case when the pole will leave the real axis. That's the case when the breakaway points exist. But in this case, there are no breakaway points. So let's try to find the angle of departure. So for example, we want to find the angle of departure for this particular point. We want to know how the locus leave that particular pole. Let's label it as theta d. So we use the relationship that we have found before, that the angle made by the vector of poles to that particular point minus the angle made by the vector of zeros to that particular point should be a multiple of 180 degrees, or you can also assume this theta d as unknown. So the angle of departure will be 180 degrees minus sum of 90 degrees. That's this particular vector made by this pole. So that will be 90 degrees. So how do we find the other angle? So for example, in this case, you can just use the inverse tangent to find the angle. So that will be the tangent of, it should be 1 over, this length is 2. Okay, so it's just, should have been 1 over 2. Okay, that was a mistake for this one. Alright, so tangent inverse of tangent 1 over 2 to get this particular angle. So again, there's another error here. It should be just 90 plus, but I will correct it later. So the next one is this 0. It should be minus. There's 1 here and there's 1 here. So it's just the inverse tangent of 1 over 1. Okay. So there's an error in the signage. So you better be careful. The angle made by the pole should all add up. Okay, this is theta p. So it should have been 90 degrees plus inverse tangent of a half minus the angle made by the vector of 0. Right? So if you do that, then it will be correct. So you will see that the angle made by the locus leaving this particular point is 108.43 degrees. So that's 90. So it's a little bit more than 90. So it's like 108 degrees from the real axis. So you go counterclockwise 108 degrees. It will leave this particular point approaching the asymptote. So you don't have to calculate for the bottom part because it's going to be the mirror image, the second rule, if you remember. Right? So that's the case when we have the angle of departure. So let's look at another example of the case when we want to sketch a root locus, but in the situation when we have a complex zeros or poles. So in this case, we have another complex poles. Okay, so this is the example that I want to discuss. We have the breakaway point at minus 2.5 as the open loop transfer function as shown here. You can see there are many poles, 1, 2, 3, 4, 5. So 5 poles and 1, 0. How can we sketch the root locus? Of course, if you have MATLAB, you just use MATLAB to do that. But let's just try to see how we can do it using just pen and paper. right? Okay, so this is the system that we have. By the way, the notes, the soft copy of these notes will be given later on, right? So if some points are not clear, then don't worry too much. Let's just try to understand the concept first. So here I'm plotting all the poles and zeros, right? That's the two complex poles that I'm going to write. That's -1 plus minus j, and then there's 1 0 at -4, yeah, -5, -3. Okay, so let's mark the location of the locus at the real axis. So remember the rule where the locus should be to the left of odd number of poles and zeros. So here there's 1, so there should be a locus here. Over here there's 2, so there's no locus here. Over here there's 1, 2, 3, so it should be a locus here. So I've marked it, the location where locus should be in the real axis. Okay, that point is easy. The locus will start at poles and at this particular 0. But here the breakaway point was given, so you can mark it right away, knowing that these two poles will meet at this particular point and leave before leaving the real axis. We know that the once we have the breakaway point, there will be a case when the pole will end at zeros. It should end at zeros, but in this case the zeros will be at infinity. So there should be asymptotes. Let's use the asymptote rule and calculate the asymptotes. Okay, first we calculate the angles as shown here. You will get should be 4 here, right? So that's another one. Okay, 45 degrees, so you substitute k from 0, 1, 2, 3, and the angles are given here, so you can draw the asymptotes. But you need to find the center of the asymptote first using the equation given in the video before. So it's the number of open loop poles minus the number of open loop zeros. That's the value of the poles minus the value of the zeros divided by the number of poles minus the number of zeros. So you have one pole 0, another one at -5, -3, and -1 plus j, -1 minus j. So let's add them all up minus the zeros. Okay, so there should be -4, right? And then again 5 minus 1, which is 4. Okay, so if you calculate this, you will get the center of the asymptote to be at -1.5. So you can mark that point and draw the asymptotes. These are if you use the protractor, so you can mark 45. So basically there are, you can see that's 1, but basically the 2 to 5 is just the other one. You can just draw the asymptotes right away. So it's good to bring this, to have the ruler and the protractor, so that you can measure the angle correctly. Remember, this is just a sketch, okay? So it doesn't have to be 100% correct. Now, how does the locus looks like? So you know that these two locus will meet at that particular point, leaving the real axis, because the breakaway point, this can be calculated, but in this case it was given, so you don't have to worry about it. But that shows that it is approaching this particular asymptote this way. But what about these two poles here? So how does the locus leave? So that's why we need to calculate the angle of departure for this particular point. So again, don't worry about some missing point here, because I will give the notes later. So again, we draw vectors from poles and zeros, and we label one angle. So angle of interest here, we want to find the angle theta d made by this particular point of the locus, leaving this pole. So using this rule, so we can calculate we need to calculate all the angles, okay? The sum of the angle made by the vector of poles minus the sum of angles made by the vector of zeros should be a multiple of 180 degrees. So you just leave out the theta d here. We assume it's very close, so we just draw the vector directly to that particular point. Alright, so we got 90 degrees for this particular theta. This vector is just a straight line made by this pole, so it's just 90 degrees. The second one is 135 degrees, made by this. It's 180 degrees minus 45 degrees, because we know this angle. This is 1, this is 1. There should be 45 degrees, so we got 135 degrees. So for the next one, this angle, so you have to calculate using the tangent, inverse tangent. So that's 1, and that's 1, 2. It's good if you can make it according to scale, so it will make it easier for you to calculate the length. So inverse tangent of half. Right, so we got 3 angles already. 1, 2, 3. So another 2. This is the final pole, angle made by the pole, theta 4. So that's 4 and 1. So it should be inverse tangent of 1 over 4. And finally, we need to find the angle made by the vector of 0 at minus 4. Okay, that's the pole. So what about the angle made by the vector of that particular 0? So again, we use the inverse tangent. That's the easiest way. That's 1 over 1, 2, 3. Should be 3. Yeah. So you just approximate it. Okay. This is a sketch anyway. Don't be too worried about the so many decimal places. Subtract the zeros. Okay. That's the angle of poles minus the 0. Plus 180 degrees. And you will get a value here. Minus 68 degrees. So you can see that it's going to be minus 68 degrees. So going clockwise is minus. So if you can mark the angle of minus 68 degrees roughly, so it's going to go down first before going up again, approaching the asymptote. Okay, so I'm drawing it that way. So it's going to be again a mirror image, so you don't have to repeat the calculation for the bottom part. So that's how the root locus will look like. Okay, I'll trace it using the, show you the pen, using the pen. You can see it approaching the asymptote, right? So that's 1, it's 2 and 3, that's 4 and 5. Remember, we have 5 poles, so we have 5 locus. You can just trace it. Okay, that's how it looks like, right? So you might want to check your answer using MATLAB. So if you plot it using MATLAB, so this is how it's look like, very similar to what we have achieved using just the pen and paper. So it's going to be, this is minus 68 degrees. That should be positive 68 degrees. We didn't calculate this point, and that will be the minus 2.5 something. And this locus starts from the pole n at 0. That's another asymptote. So there should be 4 asymptotes as shown in the sketch. So that's how it looks like in MATLAB, right? So that concludes the lecture on how to sketch the root locus. Next, we will look at how to use this root locus to actually design starting with a proportional control. Okay, so thanks for your attention. See you in the next video. Bye bye. Assalamualaikum warahmatullahi wabarakatuh.